Our galaxy holds secrets that defy everything you think you know. You look up at that pale river of stars and feel a familiar sense of awe. But the true story of the Milky Way is stranger, darker, and more magnificent than any picture can convey. We are about to journey through 25 of its most incredible and rarely discussed truths. By the end, you will never see our galactic home the same way again. We will uncover why our solar system is on a 230 million year loop, what invisible glue holds everything together, and how our galaxy grew by devouring others. What does it feel like to realize your home is a living, breathing, and cannibalistic cosmic giant? Our entire solar system is a passenger on a voyage so slow we barely notice it is happening. This is the first great secret, the rhythm of our galactic year. Every 230 million years, our sun, with every planet, moon, and asteroid in its gravitational embrace, completes one single majestic orbit around the center of the Milky Way. Think about that timescale for a moment. One galactic year, the last time our solar system was in this precise position in the galaxy, the Earth looked utterly alien. The supercontinent Pangaea was still whole, and the first dinosaurs were just beginning their tentative steps into a world dominated by earlier reptiles. In the time it takes for us to make one loop, continents have shattered and recombined. Life has risen from the seas to conquer the land and the air, and entire dynasties of creatures have come and gone. We are currently about halfway through our current orbit, cruising through a relatively calm spiral arm. But this journey is not a simple circle on a flat plane. Our solar system bobs up and down through the galactic disk like a carousel horse on a slowly undulating track, passing through different environments. Every few tens of millions of years, we might drift through a denser cloud of gas and dust or a region with more ancient stars. These changes are subtle, stretched over epochs, but they may have profound effects. Some scientists speculate that these periodic passages could influence Earth's climate by subtly altering the stream of cosmic rays reaching our planet, potentially triggering ice ages or warming periods. So while you sit still, you are, in fact, racing through the galaxy at over 500,000 miles per hour, on a journey that makes all of human history feel like the blink of an eye. We are eternal travelers on a path so vast it defies human perception. This incredible speed of our journey presents a profound puzzle. Our sun and all the stars in the outer reaches of the Milky Way are orbiting far too fast. According to the laws of gravity and the visible mass of all the stars, gas, and dust we can see, these stars should be flung out into the void like marbles spun off a plate that is not spinning fast enough. Yet they remain, held in a firm, stable embrace. The reason is our second secret, the true, dominant architecture of our home. Over 90% of the Milky Way's mass is completely invisible. We are embedded within an immense spherical halo of dark matter. This is not a cloud of normal stuff. It does not emit, absorb, or reflect any light we can detect. It is a ghostly scaffold, a cosmic skeleton made of something fundamentally unknown. Picture our beautiful, luminous galaxy of stars and nebulae that we see in photographs. Now imagine that this is just the tiny, glittering jewelry pinned to the surface of a balloon that is 1,000,000 light years across. The balloon itself, vast and invisible, is the dark matter halo. Its gravitational grip is the only thing preventing our galaxy from flying apart. We detect it not by seeing it, but by feeling its pull. Astronomers watch how stars on the outer edges of the galactic disk move, and their velocities betray the presence of this immense, unseen anchor. Without this dark gravitational glue, the spiral arms would unravel, and stars like our sun would drift away into the intergalactic darkness. Everything we consider to be the Milky Way, everything beautiful and bright, is just a minor decoration on the surface of a profound and enduring mystery. That invisible dark matter halo did not just appear, It grew, and our galaxy grew with it in a manner far more violent than its serene appearance suggests. This brings us to our third secret. The Milky Way is not a pristine, isolated island universe. It is a cosmic cannibal, a giant built by devouring its smaller neighbors. Its history is written in the scattered bones of galaxies it consumed long ago. Astronomers, acting as galactic archaeologists, have learned to read this history in the motions of ancient stars. They have found entire populations of stars moving against the flow, stars with different chemical compositions, stars that tell a story of a colossal collision billions of years in the past. The most dramatic of these ancient mergers is known as the Gaia Enceladus galaxy. It is named for the European Space Agency's Gaia spacecraft, which mapped the precise positions and motions of over 1 billion stars, and Enceladus, a giant from Greek mythology. This was no minor event. Roughly 10 billion years ago, a galaxy perhaps 1/4 the mass of the young Milky Way came screaming in on a fatal trajectory. The merger would have been a slow-motion, billion-year catastrophe, tearing both galaxies apart and reshaping them into something new. The stars from that devoured galaxy were scattered throughout the halo and the inner parts of our galaxy, like fossils embedded in stone. Today, we can still identify them. They orbit in the opposite direction to many of the Milky Way's native stars or on wildly tilted paths, and they carry a distinct chemical signature with fewer heavy elements forged in later generations of stars. This single event likely delivered a huge influx of gas and stars, fueling a burst of new star formation and probably giving our galaxy's central bulge its distinct shape. But the cannibalism did not stop there. The Milky Way's gravity continues to tear apart smaller dwarf galaxies that venture too close. We see the evidence in long, shimmering rivers of stars called stellar streams arcing across the galactic halo. These are the dissolving remains of galaxies and star clusters being stretched out by our galaxy's immense tidal forces like cosmic taffy. The most famous is the Sagittarius dwarf spheroidal galaxy, which is currently in the process of being shredded and absorbed. Its stars are being pulled into great loops around the Milky Way, a process that will take hundreds of millions of years to complete. So when you look up at the night sky, you are not looking at a static monument. You are looking at a dynamic, ever-changing structure, a palimpsest written over with the stories of conquest and assimilation. Every star you see has a lineage, and many of them are immigrants from other, now vanished galaxies. Our home is a melting pot built by violence, and its dining habits are far from over. That history of galactic cannibalism has left its permanent mark on the very shape of our home. We picture the Milky Way as a beautiful, stately pinwheel, but that classic image is subtly wrong. The truth is, we live in a barred spiral galaxy. At its very heart, hidden behind thick veils of dust, lies a dense, elongated structure of stars roughly 27,000 light-years long. This is the galactic bar. Think of it not as a rigid rod, but as a colossal, slow-motion traffic jam of stars, all orbiting together in a coordinated dance. This bar rotates as a single, coherent unit, but it spins at a different speed than the spiral arms that extend from its ends. It is the great organizer, the hidden engine driving the galaxy's grand design. Its immense gravity acts like a cosmic plow, pushing and pulling on the vast clouds of gas and dust that drift through the inner galaxy. It funnels this raw material inward toward the galactic center, feeding the hungry region around the supermassive black hole and triggering bursts of new star formation. But its most famous role is in creating the very arms we admire. The spiral arms of the Milky Way are not permanent structures made of the same stars. They are density waves like traffic jams on a celestial highway, or the spiral pattern made in a cup of coffee as you stir it. As the bar rotates, its gravitational influence creates a shock wave that compresses the interstellar gas. This compression triggers the collapse of giant molecular clouds, lighting them up with the brilliant blue light of newborn, massive stars. We see the spiral arms because that is where star birth is happening, a luminous wave propagating outward. The stars themselves move in and out of these arms as they orbit. Our own sun has likely passed through several different spiral arms during its long life, each passage potentially bathing our solar system in a slightly different radiation environment from the brilliant, short-lived stars being born there. So the majestic spirals we draw on posters are not static features but brilliant, temporary flashes, a self-perpetuating pattern orchestrated by the slow, relentless spin of that hidden central bar. It is the galaxy's heartbeat, setting the rhythm for birth and structure across the entire disk. Yet the bar's gravitational influence is not the only force sculpting our galaxy from within. The Milky Way's core holds a power so immense it can shape structures on a scale that dwarfs entire galaxies. Emanating from the very heart of our galaxy are two colossal, symmetrical bubbles of seething energy. These are the Fermi bubbles, and they are one of the most dramatic and mysterious features ever discovered in our home. Picture two vast, hourglass-shaped balloons, each one towering 25,000 light-years above and below the galactic plane. That is a quarter of the distance from Earth to the galactic center. They are invisible to the human eye, but they glow fiercely in the high-energy language of gamma rays, detected by a space telescope named for the physicist Enrico Fermi. These are not gentle structures. They are filled with ultra-hot gas, charged particles moving at nearly the speed of light, and they are blasting out a constant stream of radiation. They form a perfect, ghostly silhouette, a cosmic hourglass of pure force centered on Sagittarius, a star, our galaxy's supermassive black hole. The leading theory for their creation is as breathtaking as the bubbles themselves. Roughly 2.5 million years ago, Sagittarius, a star, may have awakened from its slumber in a spectacular fashion. It did not simply snack on a passing star. It likely experienced a colossal, explosive outburst, a hyper-energetic event where vast amounts of matter fell in and were then violently expelled in two opposing jets from its poles. This eruption would have been a titanic burp of cosmic proportions, flooding the regions above and below the galaxy with unimaginable energy. The shockwaves from that ancient cataclysm are still expanding today, carving out and inflating these immense gamma-ray balloons. They are a fossil record of a moment when the heart of our galaxy roared, but the mystery deepens. Recent observations suggest these bubbles might have a complex, layered structure with harder, more energetic edges and a slightly softer interior, hinting at multiple outbursts or a sustained period of activity. Their very presence tells us that the quiet giant at our galactic center is not always dormant. It has a violent history, and its past eruptions have physically reshaped the environment of our entire galaxy, blowing bubbles on a scale that the human mind can scarcely comprehend. We live in the lingering echo of that primeval blast, a reminder that even the most majestic structures can be born from moments of incredible violence. But those immense Fermi bubbles are not the only evidence of our galaxy's powerful exhalations. From the same chaotic heart, astronomers have detected something even more vast, a phenomenon so grand it has been called the galactic geysers. These are colossal fountains of million-degree gas, erupting from the galactic center and extending for tens of thousands of light-years, far beyond even the gamma-ray bubbles. If the Fermi bubbles are the ghostly outline of an ancient explosion, the geysers are the ongoing, energetic breath of the galaxy itself, a superheated wind blowing out into the halo. This is not a gentle stream. It is a raging torrent of material being violently expelled, likely driven by the combined energy of countless supernova explosions and the restless activity around Sagittarius, a star. This outflow is so powerful it is carving a cavity in the surrounding gas of the galactic halo, shaping the very environment our galaxy resides within. Yet for all this material rushing out, the Milky Way is also engaged in a spectacular act of cosmic recycling, and this is where the story turns toward our nearest galactic neighbors. Look toward the southern hemisphere skies, and you can see two fuzzy patches of light, the Large and Small Magellanic Clouds. These are dwarf galaxies, satellites caught in our immense gravitational pull. For billions of years, our galaxy has been engaged in a slow-motion act of theft, stretching out these companions with its tidal forces. The result is one of the most spectacular structures in the local universe, the Magellanic Stream. Picture a faint, shimmering river of hydrogen gas over 600,000 light-years long, arcing across nearly half the sky. This is not a stream of stars, but a colossal ribbon of raw, primordial gas torn from the clouds as they swing around our galaxy. This magnificent stream is now falling into the Milky Way, a slow-motion rainfall of fuel onto the galactic disk. Here lies the beautiful and violent balance of our home. While the galactic center blasts gas out in geysers and bubbles, our gravity is simultaneously pulling in a fresh supply from our neighbors. The Magellanic Stream is a direct pipeline, channeling the building blocks of future stars directly toward us. Currents of this gas are already beginning to collide with the outer regions of our own galactic disk, compressing and triggering the birth of new stellar nurseries on the fringes. We are witnessing a galactic-scale life cycle in action. The Milky Way is both a consumer and an expeller, a living system that breathes out hot gas and breathes in cold, fresh material. The very stars that may one day shine in distant spiral arms are being built right now from the remains of galaxies we are slowly dismantling. Our home does not exist in isolation. It is an active participant in a dynamic gravitational dance, forever stealing the breath from its companions to fuel its own brilliant future. This grand cosmic cycle of inflow and outflow is not the only motion dictating our fate. Our galaxy, for all its immense power, is not the master of its own trajectory. We are being pulled. Every galaxy in our local neighborhood, including Andromeda and the Milky Way, is caught in a relentless current, flowing toward a point in the darkness with a gravitational grip so strong it defies comprehension. This is the Great Attractor, and it is our frightening destination. Located roughly 250 million light-years away in the direction of the constellation Centaurus, this is not a single object but a colossal concentration of mass, a gravitational focal point so immense it is dragging entire clusters of galaxies toward it. Our local group is moving at an astonishing speed of over 1.5 million miles per hour in that direction, caught in a river of galaxies on a billion-year journey. The most unsettling part, we cannot see it directly. The Great Attractor lies directly behind the plane of our own Milky Way, in a region astronomers call the Zone of Avoidance. Here, the thick dust and dense star fields of our galaxy's central bulge blot out almost all visible light from the universe beyond, creating a blind spot in our maps of the cosmos. It is as if we are trying to see a distant city from inside a fog bank. For decades, this region was a profound mystery, a blank space on the cosmic chart hiding the very thing pulling us toward it. Through painstaking observations in wavelengths that can pierce the dust like infrared and radio waves, we have begun to lift the veil. We now know the heart of the Great Attractor is likely the Norma cluster, a massive gathering of thousands of galaxies, itself sitting at the center of an even larger superstructure called the Laniakea supercluster, of which our Milky Way is merely a distant suburb. The pull we feel is the combined gravity of this unfathomable amount of matter, hundreds of thousands of galaxies clumped together in one region of space. So while we orbit the galactic center and our galaxy dances with Andromeda, all of it is flowing down a gravitational waterfall toward a point hidden behind our own cosmic doorstep. We are passengers on a voyage whose ultimate end lies shrouded in the dust of our own making, pulled by a force whose full nature we are only beginning to glimpse. That immense pull toward the Great Attractor is not the only force powerful enough to launch objects across the cosmos. Within our own galaxy, there exists a population of celestial outlaws, stars moving so fast they are not just leaving their neighborhoods, they are escaping the Milky Way entirely. These are the hypervelocity stars, and they are the galaxy's ultimate runaways. Traveling at speeds exceeding 1 million miles per hour, they are on a one-way trip into the endless dark of intergalactic space. Their origin story is as dramatic as their speed. Most are believed to be the survivors of a cosmic slingshot event of unimaginable violence. Picture a binary star system, two stars locked in a graceful orbital dance around each other. Through some misfortune of celestial mechanics, this pair drifts perilously close to the supermassive black hole at the galactic center, Sagittarius, a star. The black hole's immense gravity violently rips the binary apart. One star is captured, doomed to orbit or be consumed by the black hole. The other, like a stone from a sling, is flung away at a staggering fraction of the speed of light. It is given so much kinetic energy that it overcomes the entire gravitational pull of the Milky Way. From that moment, its fate is sealed. It will depart the galaxy, sailing alone through the void between galaxies, a solitary traveler on an eternal journey. But these stars are more than just fascinating exiles. They serve as invaluable tools for astronomers. By tracing their paths backward across the sky, scientists can map the intricate gravitational field of the galaxy. Think of them as probes fired through the cosmic landscape. Their trajectories are bent and shaped by the mass they pass, both visible and dark. By studying how these stars accelerate and where they came from, astronomers can weigh the galaxy, testing the distribution of that invisible dark matter halo we discussed earlier. Each hypervelocity star is a messenger, its speed and path carrying encoded information about the forces that launched it and the unseen structures it passed on its way out. They are the accidental experiments of a monstrous black hole, giving us a unique way to measure the very fabric of our galactic home. So while we are pulled toward a distant attractor, our own galaxy is simultaneously firing stars into the abyss, each one a testament to the ferocious power lurking in its silent heart. Those runaway stars blaze a trail through an invisible architecture, a force field woven into the very fabric of our galaxy. This is the vast galactic magnetic field, a subtle but pervasive web of energy that stretches from the smallest dust grains to the largest spiral arms. While dark matter provides the gravitational skeleton, this magnetic field is the galaxy's nervous system, an invisible network guiding and shaping nearly everything that moves through the interstellar void. It is astonishingly weak, millions of times weaker than a common refrigerator magnet, but its influence is everywhere because it operates across such immense scales. Think of it as a whisper that, when spoken across 50,000 light-years, can move mountains of gas and steer atomic bullets. This field threads through the emptiness between stars, aligning tiny, needle-like particles of cosmic dust. These dust grains, made of silicates and carbon, spin to orient themselves with the magnetic field lines, much like countless tiny compasses all pointing in the same direction. This alignment has a direct, observable consequence. When starlight passes through these clouds of magnetically ordered dust, its light waves become polarized, vibrating in a preferred direction. By studying this polarization, the subtle fingerprint left on the light of millions of stars, astronomers can painstakingly map the magnetic field of the entire Milky Way. It reveals a stunning tapestry of lines flowing along the spiral arms, twisted into loops by supernova explosions and emanating from turbulent stellar nurseries. This magnetic web does far more than just arrange dust. It acts as a galactic highway system for some of the universe's most energetic particles. Cosmic rays, which are protons and atomic nuclei accelerated to nearly the speed of light, are not traveling in straight lines. They are chaotic, high-speed particles that spiral along these magnetic field lines, bouncing and scattering in a turbulent maze. Without this magnetic field to contain them, these rays would simply fly out of the galaxy almost immediately after their creation in supernova shockwaves. Instead, the field traps them, creating a vast, swirling sea of radiation that fills the galactic disk. This trapped radiation is a crucial part of the interstellar environment, influencing the chemistry of gas clouds and potentially even playing a role in the formation of stars by providing pressure. The field itself is dynamic, generated and sustained by the motion of charged particles in the galactic plasma, a self-perpetuating dynamo on a scale so grand it is difficult to fathom. So while we gaze at the bright stars and colorful nebulae, an unseen lattice of magnetic force is quietly at work, orchestrating the dust, channeling invisible radiation, and providing an essential scaffold for the galaxy's ongoing evolution. It is the silent conductor of the cosmic orchestra, its influence felt in the alignment of a speck of dust and the path of a particle moving at the speed of light. That magnetic web may be invisible, but the darkness it permeates is far from empty. Drifting through the immense spaces between stars are countless unseen worlds, travelers on a far lonelier path than any hypervelocity star. Astronomers now believe these rogue planets, dark worlds untethered to any sun, may outnumber the stars in our galaxy. The estimate is staggering, potentially in the billions. They are the galaxy's true silent majority, a hidden population of orphans wandering the cosmic night. Most are thought to form in one of two ways. Some begin like any other planet, coalescing from a disk of gas and dust around a young star. But gravitational tussles with sibling planets can be brutal. A close encounter can slingshot a world clear out of its solar system, ejecting it into interstellar space. Others may form more directly, collapsing on their own from small, isolated clouds of gas and dust, never knowing the warmth of a parent star. Detecting these dark, cold exiles is one of astronomy's greatest challenges. They emit no light of their own, and with no nearby star to illuminate them, they are nearly invisible. The primary method for finding them is called gravitational microlensing. When a rogue planet passes almost perfectly in front of a distant background star, its gravity acts as a tiny lens, bending and magnifying the star's light for a brief period. This creates a telltale spike in brightness, a signature that reveals the planet's presence and allows for a rough estimate of its mass. These events are incredibly rare and fleeting, but they have given us a census of the darkness. The data suggests that for every star in the Milky Way, there could be dozens of these nomadic worlds. Their existence transforms our image of a galaxy. It is not just a collection of stellar systems with planets orbiting in orderly rings. It is a sea of interstellar space thick with solitary worlds, a vast archipelago of darkness. And while most are likely frozen, icy spheres, some larger ones could retain heat from their formation or from the radioactive decay in their cores. This raises a fascinating, haunting possibility. A rogue planet with a thick, insulating ice crust might harbor a global subsurface ocean kept liquid by internal warmth. Such an ocean, sealed away from the cold vacuum of space, could persist for billions of years. In that eternal, sunless sea, around hydrothermal vents on an ocean floor that never sees sky, the chemistry for life might just be possible. They would be the ultimate lonely outposts, life existing in absolute darkness, adrift between the stars, completely unaware of the galaxy of light swirling above the ice. This means the Milky Way's potential for life may not be confined to star systems at all. It could be sailing silently in the deep freeze, waiting in the dark. The silent darkness between stars may hide rogue planets, but the frenetic core of our galaxy conceals a different kind of absence. Surrounding the supermassive black hole Sagittarius, a star is a dense, ancient swarm of millions of stars packed into a space just a few light years across. In such a stellar traffic jam, death should be a frequent and spectacular event. Massive stars there should burn through their fuel quickly and explode as supernova, leaving behind dense, city-sized corpses called neutron stars. Many of these should be pulsars, spinning rapidly and beaming lighthouse-like pulses of radio waves across the galaxy. The math is clear. Based on the sheer number of stars in that crowded core, astronomers predicted they should be able to detect thousands of these pulsars. Yet when they point their most powerful radio telescopes toward the galactic center, they find almost none. This is the missing pulsar problem, a quiet paradox in the galaxy's noisiest neighborhood. It is as if you walked into a stadium packed with people and heard only a handful of voices. Where is everyone? One compelling theory points to a cosmic smokescreen. The space between us and the galactic center is not empty. It is filled with turbulent clouds of ionized gas, swirling in the intense gravitational field of the black hole. This gas is turbulent and magnetized, and it can scatter and smear out the precise, clockwork pulses of radio waves from a pulsar, making their signals fade into the background radio static of the galaxy. The beacons are there, their messages are simply being scrambled before they can reach us. Another, more profound possibility involves the very nature of life and death in such an extreme environment. The gravitational tides near Sagittarius, a star, are unimaginably strong. It is possible that when a massive star goes supernova there, the explosion is not symmetrical. The black hole's pull might distort the dying star's final moments, causing the resulting neutron star to receive an uneven kick. This could either fling it away at high speed, ejecting it from the core region entirely, or send it careening directly into the black hole, swallowed without a trace. Furthermore, the stars in that dense cluster are old and chemically distinct, having formed billions of years ago from primordial gas. They might evolve differently, perhaps resulting in fewer supernovae that produce the classic, rapidly spinning pulsars we know how to find. This missing population is more than a celestial accounting error. Finding these hidden neutron stars is crucial because they would be unparalleled tools for testing gravity itself. A pulsar in a tight orbit around Sagittarius, a star, would allow scientists to measure the space-time warp caused by the black hole with exquisite precision, putting Einstein's theories through their most extreme exam. Their absence leaves a gap in our understanding, a silent question mark at the heart of our galaxy. What we cannot see there may ultimately teach us just as much as what we can. While the missing pulsars present a quiet mystery, other structures near the core shout their presence with violent clarity. Jutting out from the chaotic heart of the Milky Way are two colossal chimneys, immense conduits of seething energy that act as the galaxy's ultimate ventilation shaft. These are not made of brick and mortar, but of superheated plasma and tangled magnetic fields, each one a towering pathway stretching for hundreds of light years. Discovered only recently by the European Space Agency's XMM Newton telescope, these chimneys form a direct physical link between the frenetic activity around Sagittarius, a star, and the base of those immense Fermi bubbles high above. Picture them as the exhaust pipes of a galactic engine, funneling the furious output of the core up and out into the wider halo. They rise perpendicular to the galactic plane, starting from within a few hundred light years of the black hole and extending all the way to the point where the gigantic gamma-ray bubbles begin. Inside these chimneys, the conditions are extreme. Gas is heated to millions of degrees, and it is not sitting still. It is rushing upward, a supersonic wind carrying with it a torrent of magnetic energy and a flood of high-energy cosmic rays. This outflow is a critical piece of the galaxy's energy budget, a regulated release valve for the immense forces generated in the core. Without these chimneys, that energy might remain trapped, building up until it erupts in a far more catastrophic, less controlled explosion. Instead, they provide a steady, structured pathway. They are the channels through which the magnetic field, generated by the turbulent motions of gas near the black hole, gets transported upward, helping to inflate and shape the Fermi bubbles themselves. Think of it as the galaxy's circulatory system for raw power. The cosmic rays accelerated in supernova shocks near the core are guided up these magnetic chimneys, preventing them from simply bouncing around chaotically in the inner galaxy and instead launching them on a journey into intergalactic space. This process does more than just vent energy. It actively shapes the environment for light years around. The chimneys are carving cavities in the surrounding cooler gas, and their outflow may be triggering star formation along their walls by compressing interstellar material, even as they blast other gas away. They reveal a galaxy that is not just a collection of stars, but a finely tuned thermodynamic engine. The core generates a storm of energy, and these newly discovered structures are the ducts that carry that storm safely away, proving that even in the chaos of a galactic center, there is an underlying architecture, a method to the madness that governs the life of our Milky Way. Amidst the violent energy chimneys and the silent drift of rogue planets, the galaxy's most profound work happens in places of deep cold and profound darkness. These are the galactic molecular clouds, the true cradles of creation. They are not mere voids between stars, but colossal, structured entities, the maternity wards where stars are born. To stand within one would be to experience an eternal, frozen night, where temperatures hover just a few degrees above absolute zero, and the density is 1,000,000 times greater than the surrounding space. Yet within this frigid gloom lies the raw material for everything luminous in the galaxy. Take the Orion Molecular Cloud Complex, a vast stellar nursery over 1,000 light-years away that gives us the iconic Orion Nebula. That beautiful, glowing gas cloud is just a tiny blister on the surface of a far greater darkness, a small region where newborn stars have lit up their surroundings. The cloud itself extends for hundreds of light-years and contains enough gas and dust to form tens of thousands of stars like our Sun. These clouds are primarily composed of molecular hydrogen, two hydrogen atoms bonded together, along with sprinklings of helium and that all-important cosmic dust. The dust is the secret ingredient. These microscopic grains, smaller than a particle of smoke, act as a shield, blocking the harsh ultraviolet light from distant stars and allowing the interior of the cloud to remain profoundly cold. This cold is essential because it lowers the internal pressure. Gravity can then begin its slow, inexorable work, causing denser patches within the cloud to start collapsing under their own weight. The process is not a simple crunch. The cloud is turbulent, swirling with internal motions, and laced with magnetic fields that provide support against collapse. It is a cosmic tug-of-war. Eventually, in the densest knots, gravity wins. A core condenses, spinning faster as it shrinks, flattening into a disk. At the center of that disk, pressure and temperature soar until nuclear fusion ignites and a star is born. But these clouds are more than just star factories. They are also cosmic chemistry sets. Within their icy dust grains, in the cold and dark, simple atoms link together to form complex molecules. Astronomers using radio telescopes have identified over 200 different molecular species floating in these clouds. We find water, ammonia, and formaldehyde. We find alcohols like ethanol and sugars like glycolaldehyde. Most intriguingly, we find long chains of carbon-based molecules, the precursors to amino acids, the building blocks of proteins. The same fundamental organic chemistry that led to life on Earth is happening in the frozen depths of space, written in the silent radio whispers of these dark clouds. Every ingredient in your body, every carbon atom in your DNA, was forged in a star and likely once passed through the icy matrix of a cloud like this. These vast, cold structures are not just where stars begin. They are where the very chemistry of possibility is written in darkness, long before the first light of a new sun shines. That profound chemistry written in darkness takes shape within a structure we often imagine as perfectly flat. But our galaxy's disk is not the pristine, rigid platter we see in illustrations. It is twisted, bent, and flaring at the edges, a dynamic shape revealing a history of gravitational turmoil. This warp is not a small imperfection. If you could view the Milky Way from the side, from a distance of hundreds of thousands of light years, you would see its entire disk of stars and gas contorted into a gentle S-shaped curve, like a vinyl record left too long in the sun. The outer regions, tens of thousands of light years from the center, are pulled upward on one side and downward on the other, a colossal distortion spanning the entire galaxy. What force could possibly bend something so immense? The primary suspect is the ongoing gravitational tug of war with our orbiting satellite galaxies, particularly the large and small Magellanic Clouds. As these dwarf galaxies swing around the Milky Way, their combined gravity pulls on the dark matter halo that cradles our disk. Think of it like a spinning top. If you place a heavy weight near its rim, the top will begin to wobble, its axis tilting and precessing. The dark matter halo responds to the passing galaxies, and that motion is transmitted to the visible disk of stars and gas, setting the entire massive structure into a slow, cosmic wobble that manifests as the warp. But there is more. The very edges of the galactic disk are not sharp. They flare outward, becoming thicker and more diffuse, like the flared cuff of a sleeve. This is likely due to the diminishing gravitational grip of the galaxy's core on its outermost stars and gas. With less force holding them tightly to the central plane, these outer regions puff up, mixing with the sparse populations of the galactic halo. Mapping this intricate, three-dimensional shape has been a monumental task, made possible only recently by missions like Gaia, which provide precise distances and motions for over 1 billion stars. By plotting these stars, astronomers have constructed a three-dimensional map of the warp's current state, and they can even trace its slow rotation around the galactic center. This is far more than just celestial cartography. The precise shape and motion of the warp act as a forensic tool. Because the warp is caused by gravitational interactions, its characteristics allow scientists to weigh the Magellanic Clouds and, more importantly, to map the distribution of the dark matter halo itself. The way the disk bends tells us how the invisible mass is arranged around us. A different dark matter distribution would produce a different warp. So this beautiful, subtle distortion, this grand bend in the road of stars we travel, is a direct message from the unseen 90% of our galaxy's mass. It is a signature of past and present collisions, a wobble in the dark, reminding us that our home is not a static monument, but a flexible, responsive structure, still ringing from ancient impacts and the constant pull of its companions. Our galaxy's warp is a slow, majestic bending, but astronomers have now discovered something far more rapid and startling rippling through the disk. The Milky Way is not just bent. It is vibrating. Millions of stars are not following the smooth, predictable orbits we once assumed. Instead, their motions reveal a series of colossal ripples, like waves from a stone dropped in a pond, propagating outward through the stellar sea. This is galactic seismology, and it tells us our home is still ringing from a recent, violent impact. The most prominent of these waves was uncovered by the Gaia spacecraft, which showed entire populations of stars above and below the galactic plane moving in coordinated, wave-like patterns. If you could speed up time, you would see sections of the disk oscillating up and down, as if the entire structure were breathing. The leading cause of this stellar tremor is almost certainly a close encounter with the Sagittarius dwarf spheroidal galaxy, that same satellite we are slowly tearing apart. While the Magellanic Clouds cause the long-term warp, the smaller Sagittarius galaxy seems to be responsible for these sharper, more recent ripples. Astronomers believe that within the last few 100 million years, perhaps as recently as when dinosaurs still walked the Earth, this dwarf galaxy made an especially close pass, plunging through the outer regions of our galactic disk. It did not simply pass by, it plunged through like a ship plowing through water, its gravity violently disturbing the orbits of hundreds of millions of stars in its wake. The stars themselves were not physically shoved upward. Instead, the dwarf galaxy's gravity delivered a powerful kick to their collective motion, setting them into an oscillating pattern that will take billions of years to settle. We are seeing the aftermath of that celestial collision, the expanding ring of disturbance it left behind. These ripples are more than just a curiosity. They are a powerful diagnostic tool, allowing scientists to weigh the Sagittarius dwarf and, more importantly, to measure the density and properties of the dark matter halo. The way the waves propagate depends on the gravitational environment they move through. By studying their speed and shape, astronomers can probe the invisible scaffolding of our galaxy in a whole new way. It also reveals a Milky Way that is astonishingly responsive. A relatively small galaxy, perhaps only a 10,000th of our mass, can set the entire disk ringing, a testament to how delicately balanced and dynamically alive this colossal structure truly is. Our solar system, far from the turmoil, likely rides these waves gently, bobbing up and down by a tiny amount over eons, a subtle motion written into the future of every star in our neighborhood. This galactic ringing from ancient collisions has left its most permanent mark at the very center of our home. While our spiral arms are alive with young, blue stars and glowing nebulae, the heart of the Milky Way is a different world entirely. Here lies the galactic bulge, a colossal, football-shaped swarm of tens of billions of stars, packed into a region only about 10,000 light-years across. This is not a place of recent birth, but a museum of antiquity. The stars here are predominantly old, often many billions of years older than our Sun, and they glow with a cooler, redder hue. They are the galaxy's first citizens, the foundational population that formed during the Milky Way's most chaotic early era. Their chemistry tells this ancient story. Compared to stars in the disk, bulge stars are metal-rich, but in a specific way. They contain higher proportions of elements like magnesium and silicon, forged in the rapid, violent explosions of the universe's very first generation of massive stars. This distinct signature is a fossil record, proving that the bulge formed in a frantic, intense burst of star formation long before the orderly disk we inhabit even existed. But the bulge is not a simple, smooth ellipsoid. Recent observations suggest its inner structure is far more complex and stunning. It appears to be shaped like a giant X, a peanut-shaped or boxy core that is the natural three-dimensional endpoint of a buckling galactic bar. Imagine that central bar of stars we discussed earlier. As it rotates and interacts with itself, it can become unstable vertically, puffing up stars above and below the plane, creating this distinctive X-shaped structure when viewed from the side. We are essentially seeing the thickest, most crowded part of the bar, the galactic core's true backbone. This shape is not static. It is a dynamic, evolving structure, and its very existence helps lock in the bar's stability, governing the flow of gas and the rhythm of star formation across the entire inner galaxy. This ancient stellar metropolis plays a crucial role in the galaxy's present-day mechanics. The immense collective gravity of the bulge's billions of stars dominates the inner galactic landscape. It acts as a deep well, a gravitational anchor that helps maintain the bar's structure and influences the orbits of everything that ventures near, including the dense molecular clouds that spiral inward from the disk. While new star formation is rare in the bulge itself, the environment is too chaotic and the gas is too hot. It is the ultimate regulator. By funneling gas toward the center, it feeds the region around the supermassive black hole and influences the very activity that creates those colossal chimneys and Fermi bubbles. The bulge is the silent, ancient king, whose gravitational decrees shape the activity of the entire inner kingdom. Studying these old stars is like reading the first chapter of the Milky Way's autobiography. Their motions are different, often following more random, plunging orbits through the bulge rather than the orderly circular paths common in the disk. By decoding their light, astronomers can determine not just their age and composition, but also their trajectories. This allows scientists to rewind the cosmic clock, piecing together how this dense central structure assembled. Was it built primarily from the early, rapid collapse of a single giant gas cloud? Or was it largely assembled through the mergers of smaller proto-galaxies like the Gaia Enceladus event, whose stars were dumped into the center? The answers are written in the subtle differences between groups of bulge stars. Some populations may be true natives, born in the initial fiery genesis of the galaxy. Others might be immigrants, captured from devoured companions and dragged down to the crowded core over billions of years. Each star is a witness, and together they hold the untold story of our galaxy's violent, brilliant, and foundational youth. That ancient bulge may be the galaxy's stable core, but its gravitational influence extends far beyond the visible disk, commanding a retinue of smaller galaxies. Yet these satellites, the dozens of dwarf galaxies orbiting the Milky Way, present a mystery that has cosmologists deeply puzzled. They are not scattered randomly around us like bees around a hive. Instead, a significant number of them, including the Magellanic Clouds and many fainter dwarfs, appear to orbit in a startlingly thin, coherent plane, a vast, rotating disk of satellite galaxies. This alignment is so precise it defies the most fundamental predictions of our standard model of cosmology. According to our best simulations of how dark matter structures the universe, these small galaxies should be distributed in a roughly spherical swarm, each following its own independent, chaotic orbit. They should look like a cloud of gnats, not a set of marbles rolling on a single, gigantic plate. The probability of such a neat alignment happening by pure chance is astronomically low, less than 1 in 100. This is the disk of satellites problem, and it suggests we might be missing something crucial about how galaxies form or how dark matter behaves. One possibility is that this is a rare but not impossible fluke, a cosmic coincidence that our particular Milky Way just happens to exhibit. Yet even this explanation feels unsatisfying, as similar planes of satellites have been tentatively spotted around our neighboring galaxy, Andromeda. If it is not a fluke, then the implications are profound. It could mean that these satellite galaxies did not form independently and then get captured. Instead, they might have formed together, all from the same colossal filament of gas and dark matter that fell into the young Milky Way billions of years ago, like beads strung on a cosmic thread that later settled into a rotating plane. This would challenge aspects of the cold dark matter model, the leading theory for cosmic structure. Some theorists propose it might point to a different kind of dark matter, perhaps a warm or interacting variety that would form such filamentary structures more easily. Others suggest it reveals a more dynamic, interconnected history than our simulations capture, where groups of dwarf galaxies fall in together, preserving their alignment. This perplexing disk is more than a celestial curiosity. It is a direct observational clue, a pattern in the sky that our most successful theories struggle to reproduce. Solving it could force us to rewrite the rules for how the largest structures in the universe assemble themselves, all by studying the unexpected, orderly dance of the Milky Way's tiniest companions. This grand recycling of matter is the galaxy's hidden lifeblood, a continuous fountain of gas that keeps the entire system alive, while the chimneys vent energy from the core and the Magellanic Stream brings in fresh supplies. A more fundamental cycle is at work in the disk itself. This is the galactic fountain, and it is how the Milky Way breathes. The engine of this cycle is the death of stars. When massive stars reach the end of their lives, they do not fade quietly. They explode as supernova, and even during their lives, they blast out powerful stellar winds. These cataclysmic events do more than just create beautiful remnants and scatter heavy elements. They inject enormous amounts of energy into the surrounding space, heating the thin interstellar gas to millions of degrees and launching it outward at tremendous speeds. This hot, tenuous gas does not simply mix with the cooler material around it. Instead, it erupts upward, punching out of the thin galactic disk and into the much more diffuse halo that surrounds it. Picture a pot of water coming to a rolling boil with bubbles of steam rising to the surface and bursting. On a galactic scale, these are bubbles and plumes of million-degree plasma, rising thousands of light-years above the starry plane. Once in the halo, far from the energetic turmoil of the disk, this hot gas begins a slow transformation. It radiates away its heat, cooling over millions of years. As it cools, it condenses into denser clumps and filaments. Now, under the renewed pull of the galaxy's gravity, these cooler clouds begin a long, slow fall back down toward the disk. We see them as high-velocity clouds, massive streams of primarily hydrogen gas plummeting toward the starry plane at speeds of dozens of miles per second. They often appear as faint, shadowy blobs against the brighter radio background of the galaxy. When one of these clouds eventually collides with the galactic disk, it delivers a payload of fresh, cool, metal-enriched gas, the perfect fuel for the next generation of stars. This is not a one-time event, it is a constant galaxy-wide process. In one region, a supernova might be blasting gas out. In another, a rain of cooled gas is falling in. This cycle accomplishes several vital tasks. First, it continuously stirs the interstellar medium, preventing it from becoming stagnant. Second, it transports heavy elements forged in stellar cores and supernova explosions out into the halo, where they cool and mix, ensuring that new stars form from gas that is chemically enriched. Our own Sun and the planets around it were made from gas that had been through many such cycles, seeded with the iron, carbon, and oxygen necessary for rocky worlds and life. Without this fountain, the galaxy would slowly suffocate. The raw material for new stars would remain locked in cold clouds in the disk, eventually becoming so polluted with heavy elements that star formation would stall. The fountain vents the hot, metal-rich gas, allows it to purify and cool in the halo, and then returns it as a life-giving rain. It is the galaxy's respiratory and circulatory systems combined, an exhale of hot, spent breath followed by a deep inhale of cool, revitalizing air. This eternal rhythm, written in the rise and fall of invisible gas, is what allows the Milky Way to keep turning its dust into stars and its stars into the seeds for worlds. While that galactic fountain cycles material for new suns, the stars it creates are not all like our own. The brilliant yellow stars that dominate our night sky are a galactic minority. The true rulers of the Milky Way are small, dim, and incredibly patient. Red dwarf stars, also known as M-dwarfs, are the galaxy's silent majority, accounting for roughly 3 out of every 4 stars in our entire galaxy. Their numbers are staggering, likely exceeding 200 billion, yet you will never see one with your naked eye. They are too faint, glowing with a deep, ruddy light that is a fraction of our sun's brilliance. Their commonness, however, is matched by their endurance. A red dwarf is the ultimate marathon runner of stellar evolution. With masses between about 8 and 50% that of our sun, they burn their nuclear fuel with a slow, miserly frugality. Their cores churn with convection, constantly mixing fresh hydrogen into the furnace, allowing them to burn for trillions of years. The universe itself is only about 13.8 billion years old, which means not a single red dwarf has ever died of old age. Every one that has ever formed is still shining today, and they will continue to shine long after stars like our sun have faded into white dwarf embers. This incredible longevity means they offer stable homes for unimaginably long periods, a tempting prospect for any potential life. And where there are stars, we now know there are often planets. The Kepler Space Telescope revolutionized our understanding by revealing that planetary systems are not the exception, but the rule. Around red dwarfs, this rule holds especially true. It appears that small, rocky worlds are extraordinarily common in their gravitational spheres. Because these stars are so dim, their habitable zone, the orbital distance where liquid water could exist on a planet's surface, is incredibly close in. A planet would need to orbit its dim red sun in a matter of days or weeks to receive enough warmth. This proximity creates a profound and challenging relationship. The gravitational lock is intense. Just as our moon always shows the same face to Earth, a planet in the habitable zone of a red dwarf is almost certainly tidally locked, with one hemisphere in permanent daylight and the other in endless night. This presents a dramatic climate puzzle, with the day side potentially scorching and the night side freezing, though a thick atmosphere could theoretically redistribute heat. But the greatest challenge may come from the star's temperament. Young red dwarfs are notoriously volatile. They are prone to frequent, powerful flares, sudden eruptions that can blast their planets with doses of ultraviolet and X-ray radiation hundreds of times more intense than anything Earth receives from the Sun. These flares could strip away a young world's atmosphere, sterilizing its surface. This has sparked a fierce and ongoing debate in astrobiology. Are red dwarf systems cosmic dead zones where life is repeatedly scrubbed away by stellar tantrums? Or are they hidden gardens where life could find a way in subsurface oceans, beneath protective ice, or by evolving robust biological defenses? The sheer number of these stars and their planets makes the question inescapable. If even a small fraction of red dwarf worlds are habitable, then the most common abodes for life in the Milky Way are not around suns like our own, but in the dim, crimson light of these ancient, patient dwarfs, in orbits so tight a year passes in less time than a month on Earth. Our solar system's journey through the galaxy is not a solitary one. We are traveling within a distinct and brilliant local neighborhood, a ring of young, massive stars and stellar nurseries that encircles us at a dramatic angle. This is the Good Belt, a tilted disk of stellar activity about 3,000 light-years across, and it shapes the very sky above our heads. Look toward the constellation Orion, with its brilliant blue giants and glowing nebula. Gaze at Scorpius or the bright stars of the Southern Cross. These are not randomly scattered across the heavens. They are part of this local ring, a structure that is inclined by about 20 degrees to the main plane of the Milky Way. For a long time, astronomers noticed that many of the brightest stars in our sky seem to trace a great circle across the sky, and we now know this circle is the Good Belt's projection. It is as if our solar system is sitting inside a giant, slightly warped hula hoop made of brilliant stars and pink clouds of star-forming gas. But what created this magnificent, tilted ring in an otherwise flat galactic disk? The leading theory points to a colossal accident millions of years in the past. A massive cloud of interstellar gas, perhaps several million times the mass of our Sun, may have collided with the galactic disk in our region. The impact, like a stone dropped into a pond, sent ripples through the surrounding material, compressing vast reservoirs of gas and triggering a wave of star formation that propagated outward in a ring. Alternatively, it could have been the shock wave from a nearby supernova chain reaction, a stellar domino effect that lit up our corner of the galaxy. The result is the stellar architecture we see today. The Good Belt is not just a collection of pretty stars, it is an active, evolving structure. Within it lie some of the galaxy's most famous and studied stellar nurseries: the Orion Molecular Cloud, the Rho-Ophiuchi Cloud Complex, and the Taurus Molecular Cloud, where our own Sun may have formed long ago. These regions are hotbeds of creation, where the intense radiation and winds from the belt's massive, short-lived stars are constantly sculpting their surroundings, triggering new births or dispersing gas to halt them. This local ring is also a cosmic clock, because the stars within it are predominantly young, many only tens of millions of years old. The Good Belt itself is a transient feature. Its brilliant blue stars will burn out quickly in cosmic terms, and within a few 100 million years the belt will fade from view, its stars dispersed by their own motions. For now, however, it provides a unique laboratory. Its proximity allows astronomers to study the entire life cycle of stars and their environments in exquisite detail, from the collapse of a dense cloud core to the explosive death of a massive star, all within our own celestial backyard. The Good Belt reminds us that even on the scale of a galaxy, local history matters. The spectacular constellations that have guided and inspired humanity for millennia are not just random dots. They are the glowing signature of a specific, violent event that shaped our immediate cosmic environment, a temporary ring of fire through which our sun quietly travels. Our sun's fortunate position within the Good Belt is just one layer of a much deeper cosmic privilege. The very orbit of our solar system places us within a narrow, life-friendly band known as the galactic habitable zone. This is a startling idea. Just as a planet needs to orbit within a star's habitable zone for liquid water, a star system itself must reside in the right part of a galaxy for complex life to have a chance. The Milky Way is not uniformly hospitable. Its vast expanse is divided into regions of profound danger and profound poverty, with only a delicate ring offering the conditions for stability over billions of years. At the galactic center, the environment is lethally intense. The density of stars is staggering, increasing the probability of a nearby supernova whose radiation could sterilize planets. The powerful radiation from Sagittarius, a star, and the frenetic activity of the core bathe the inner regions in X-rays and cosmic rays. Furthermore, the gravitational chaos from so many close stellar encounters could easily destabilize planetary orbits, flinging promising worlds into the cold void or sending them spiraling into their sun. Life there would face an eternal cosmic bombardment, a constant reset button on evolution. On the opposite extreme, the galaxy's outer reaches are too quiet, and in their silence lies a different kind of poverty. Stars in the far galactic suburbs formed from gas that was never enriched with heavy elements from earlier generations of stars. Astronomers call this low metallicity. These distant stars and their planets would lack the abundant iron, silicon, carbon, and oxygen necessary to form rocky, Earth-like worlds. You might get gas giants or small, barren rocks, but the complex chemistry that leads to continents, oceans, and potentially life would be in desperately short supply. The sweet spot, the galactic habitable zone, is a ring roughly between 25,000 and 30,000 light-years from the center, encompassing perhaps only 10 to 20% of the galaxy's stars. Here, the stellar density is low enough to avoid frequent catastrophic events, yet the metallicity from generations of past stars is high enough to seed the formation of robust terrestrial planets. Our solar system orbits about 27,000 light-years from the center, placing us almost perfectly in the middle of this galactic Goldilocks zone. We are far enough from the chaotic core to enjoy relative peace, yet close enough to have formed from gas rich in the elements of life. This privileged address is not a permanent guarantee, however. As our sun continues its grand orbit, it slowly moves through different galactic environments. While we currently cruise through a relatively benign spiral arm, our path has taken us through denser regions in the past and will do so again in the distant future. Some scientists suggest these passages, which coincide with periods of increased comet impacts or cosmic ray flux on Earth, could be linked to mass extinction events in our planet's deep history. Our position is a temporary alignment of cosmic good fortune, a stable platform that allowed life on Earth the uninterrupted billions of years it needed to evolve from single cells to conscious beings gazing back at the stars. It means that when we look up at the Milky Way's shimmering band, we are not just looking at our home galaxy. We are looking out from within a narrow, sheltered corridor, a rare, safe neighborhood in a vast and often dangerous metropolis. This galactic safe zone, however, is not a permanent sanctuary. Our entire neighborhood, the Milky Way itself, is on an inescapable collision course with destiny. In roughly 4.5 billion years, our galaxy will begin a slow-motion, breathtaking dance of destruction and creation with our largest neighbor, the Andromeda galaxy. This is not a possibility, it is a certainty measured by the relentless pull of gravity. Right now, Andromeda is racing toward us at about 250,000 miles per hour, a closing speed that seems impossible until you realize the vast distance it must cross. For eons, the two spiral giants have been falling toward each other, drawn together by their mutual gravity and the dark matter halos that surround them. The first direct approach will be a glancing blow, a gravitational sideswipe that will utterly transform the night sky from any world that still exists. If you could stand on Earth at that distant time, the approach would be a spectacle unfolding over millions of years. Andromeda, currently a faint, fuzzy smudge in the constellation of the same name, would swell into an impossible, glorious presence. It would first become a distinct oval, then a sprawling disk of light rivaling the full moon, and finally a brilliant, structured whirlpool of stars that dominates the heavens. As the galaxies first pass through each other, their disks, made mostly of empty space, will ghost through one another. The chance of any two stars colliding is astronomically small. But gravity is the true artist of chaos. While stars may not crash, their orbits will be violently rewritten. The majestic spiral arms of both galaxies will be torn into long, shimmering tidal tails of stars, flung out into the darkness like cosmic ribbons. The night sky would become a canvas of unparalleled chaos and beauty, filled with streams of alien suns and glowing nebulae ignited by the gravitational turmoil. This first passage will not be the end. The two galaxies, now gravitationally wounded and intertwined, will slow, reverse, and fall back toward each other for a second, more definitive merger. Over the course of 1 billion years, this cosmic waltz will repeat, each pass stripping away their elegant spiral structures and mixing their stellar populations. The supermassive black holes at their hearts, Sagittarius, a star, and its Andromeda counterpart, will begin their own deadly duel, sinking toward the center of the new, combined galaxy through a process called dynamical friction, stirring up stars around them. Eventually, the dance will cease. The two distinct spirals will be no more. In their place will rise a single, massive, and relatively featureless elliptical galaxy. Astronomers have already given this future titan a name, Milkdromeda. It will be a redder, older stellar city, its gas exhausted by a final burst of star formation triggered by the merger, its stars following random, plunging orbits instead of the orderly rotation of a disk. Our own sun, if it still shines, will likely be flung into a much wider, more chaotic orbit within this new giant, far from the galactic core it once circled. The familiar band of the Milky Way will be gone forever, replaced by a diffuse, golden glow of blended starlight. This future is written in the laws of physics, a reminder that even the grandest structures we see today are temporary arrangements in an ever-changing universe. Our galaxy's story does not end in solitude, but in a magnificent, fiery embrace that forges a new chapter in the cosmic ledger. The future of Milkdromeda is written in the ancient past of stars we can see today. To uncover the deepest history of our galaxy, astronomers have become cosmic detectives, practicing a science known as galactic archaeology. Their evidence is not buried in rock, but in the light of the oldest suns. Every star is a chemical fossil, its atmosphere preserving a precise record of the elements present in the cloud from which it was born. By decoding this stellar DNA, we can trace lineages back billions of years. The most ancient relics are found not in the busy disk, but in the sparse galactic halo, that vast spherical cloud of stars surrounding the Milky Way. These halo stars are the galaxy's first citizens, and they tell a story of a violent, primordial beginning. They move on wildly eccentric orbits, plunging through the galactic plane on long, looping trajectories that speak of a time before the orderly disk settled into its graceful rotation. More telling than their motion is their chemistry. When you analyze their light, you find they are metal poor. In astronomy, a metal is any element heavier than hydrogen or helium. These heavier elements, carbon, oxygen, iron, silicon, are forged in the nuclear furnaces of stars and scattered into space when those stars die. The first generation of stars formed from the pristine hydrogen and helium left over from the Big Bang. When those massive pioneers exploded, they seeded the cosmos with the first sprinkling of metals. The next generation of stars formed from this slightly enriched gas. So, a star's metallicity is a cosmic birth certificate. A very low metallicity means it formed from nearly pristine gas, marking it as incredibly ancient. The halo is filled with such stars, some with metal contents hundreds of thousands of times lower than our Sun. They are living relics from the Milky Way's chaotic infancy, perhaps over 13 billion years old. By mapping the positions, motions, and chemistries of millions of these stars, galactic archaeologists can perform a kind of cosmic genealogy. They can identify distinct families. One group of ancient, metal-poor stars might all move together on a similar path, a ghostly stream that is the remains of a dwarf galaxy consumed 10 billion years ago. Another family, with a slightly different chemical fingerprint, might represent the native population that formed as the Milky Way's own dark matter halo first collapsed. This painstaking work allows scientists to rewind the movie of our galaxy's assembly. We can see not just the major mergers like the Gaia-Enceladus collision, but also the quieter, early accretion of countless smaller building blocks. Each ancient halo star is a time capsule, holding within its spectral lines the exact conditions of a long-vanished cloud in the young universe. Their silent testimony is rewriting our understanding of how a majestic spiral galaxy like ours emerges from the formless dark of the early cosmos, built star by stolen star. That stellar archaeology reveals a galaxy built from countless pieces, but some of the most influential pieces might still be out there, hiding in the darkness. Our own solar system holds clues that point to a massive, unseen presence in the galactic outskirts. For years, astronomers have been puzzled by the peculiar orbits of a handful of small, icy bodies in the distant Kuiper belt far beyond Neptune. These objects do not scatter randomly. Instead, their elongated paths seem to be mysteriously clustered, as if something very large is herding them, tugging on their trajectories with a persistent gravitational hand. The hypothetical explanation is known as Planet 9. This would not be a small, rocky world, but a potential super-Earth or mini-Neptune, perhaps 5 to 10 times the mass of our own planet, orbiting the Sun on a wildly stretched path that takes 10 to 20,000 years to complete. Its gravitational influence, the theory suggests, is what organizes these distant icy orbits. While the search for this phantom planet continues, its proposed existence echoes a much grander galactic-scale mystery. Some scientists have looked even farther out, into the halo of the Milky Way itself, and wondered if an entire unseen dwarf galaxy, nicknamed Galaxy X, could be lurking in the shadows. Just as the Magellanic Clouds tug on our galaxy and create its warp, a hidden satellite galaxy made mostly of dark matter could be orbiting us, its gravity subtly distorting the outer gas disk of the Milky Way and perhaps even influencing the cloud of comets at the very fringe of our solar system. The evidence is tentative, a faint ripple in the hydrogen gas at the galaxy's edge that might be explained by a close pass from such a dark, massive object. These two ideas, Planet 9 and Galaxy X, are separate hypotheses, one within our solar system and one far beyond it, yet they are connected by a profound and thrilling possibility. They both suggest that our cosmic neighborhood is still being shaped by hidden giants. Whether it is a lone, frozen world in the Sun's distant grasp or an entire ghost galaxy of dark matter sailing silently by, the Milky Way is not a static map. It is a dynamic puzzle, and we are still discovering the pieces, some of which might be so dark and distant we can only infer their presence by the gentle sway of the objects we can see. Finding either one would be a monumental discovery, proving that even in our own celestial backyard, the greatest influences can remain unseen, waiting in the vast dark to be revealed. This final secret brings us back to the very image we started with, that majestic pinwheel of stars. But what if that classic picture of our galaxy is not just beautiful but also surprisingly rare? For decades, astronomers have classified spiral galaxies into two broad families. On one side are the flocculent spirals. These galaxies look soft and fluffy, their arms broken into countless feathery fragments and starry patches like clouds scattered across the sky. They lack the dramatic, sweeping structure we often associate with a classic spiral. On the other side are the grand design spirals. These are the poster children of the cosmos, boasting two long, luminous, and exquisitely defined arms that coil outward from the core in a near-perfect symmetrical pattern. They are the cosmic equivalent of a meticulously engineered bridge, all graceful arcs and clear intention. For a long time, placing the Milky Way in one of these categories was guesswork because we are stuck inside it. We could not step back and take the picture, but thanks to decades of painstaking radio astronomy, mapping the distribution of gas and young stars, a compelling portrait has emerged. The evidence now strongly suggests we belong to the grand design family. Our galaxy appears to be dominated by two primary spiral arms, the Scutum Centaurus arm and the Perseus arm, that stem from the ends of that central bar. These are not faint suggestions, but massive, coherent structures, lanes of dense gas and brilliant stellar nurseries that give the Milky Way its architectural backbone. This realization carries a profound implication. Grand design spirals like ours may be the minority. Many, perhaps most, spiral galaxies are the flocculent type, their structure more haphazard and fragmented. The majestic, two-armed symmetry we cherish might be a special case, a product of a specific and stable relationship between a strong central bar and a steady supply of orbiting gas. It requires a delicate balance to maintain those clean, continuous arms over billions of years. So when you picture our galaxy, you are not just picturing home. You are likely picturing one of the universe's more refined works of art, a galactic cathedral of spiral structure. Its grand design is a testament to the specific, dynamic history that shaped it, the mergers that built its bar, the gas it stole from neighbors, and the quiet gravitational rhythms that organize its stars. In a cosmos filled with beautiful accidents, the Milky Way might just be a masterpiece of deliberate cosmic architecture. The grand design we call home is not a serene island, but a living, breathing, and often violent entity. From our solar system's 230 million-year orbit to the cannibalistic mergers that built the galactic bulge, from the invisible grip of dark matter to the chimneys venting fury from the core, each secret reveals a layer of staggering complexity. We have wandered through rings of fire like the Good Belt, sailed past rogue planets adrift in darkness, and felt the pull of a hidden great attractor. We have seen how our galaxy breathes through fountains of hot gas and drinks from streams stolen from its neighbors, all while preparing for a colossal future merger that will erase its spiral form forever. This journey through 25 revelations dismantles the simple picture of a static swirl of stars. In its place stands a dynamic, wondrous, and relentless cosmic engine, a place of ancient fossils and future cataclysms, where the potential for life huddles around tiny red suns and the architecture of reality is tested by missing pulsars and perplexing disks of satellite galaxies. Every pinpoint of light holds a story, and every dark space hums with unseen force. So the next time you find yourself under a clear, dark sky, look up at that pale river of stars. See it not as a distant backdrop, but as our home, a cannibal, a sculptor, a breather, a time capsule, and a traveler on an infinite journey. Let us know in the comments which one of these 25 secrets changed your view of the Milky Way the most. If you want to keep exploring the cosmos with us, subscribe for more deep dives into the universe's greatest mysteries. Look up and see it all with new eyes.